Okay. So starting chapter 10, introduction to hypothesis testing. Chapter 10 can seem a little confusing at first because it's a kind of a long process we're working through, but hold on, ask questions, we'll get through it. So a hypothesis is a statement we're making about the parameter. And remember that a parameter is a characteristic of the population, like the population mean or the population proportion, as compared to a statistic, which is about the sample. A hypothesis test is a procedure used to test hypotheses using sample data and probability. So here is Sam's hypothesis. Sam's hypothesis is the average weight of student laptops is 3.5 pounds. And you think it's less. So how are you going to go from here? Well, how much doubt would you have in Sam's hypothesis if you knew there was a sample of 20 student laptops weighing an average of 3.4 pounds?
Minimal doubt.
Yeah, because 3.4 and 3.5 aren't that far away, right? So you'd have some doubt, but it's like 20 laptops that are smaller and they're just barely smaller. Not a lot of doubt. Well, how much doubt would you have if you knew there was a sample of 20 student laptops weighing an average of 3.3 pounds? It's a little bit smaller, but it's still only 20 and it's not that much smaller. So it could just happen to be you ran into people with smaller laptops. But what about a sample of 20 student laptops and they weighed an average of 3 pounds? How much doubt would you have? You'd probably have a little more doubt because 3 is significantly different than 3.5. So the idea is, how do you decide where that doubt is? When do you say, well, that's enough evidence? That's what hypothesis testing does. It takes a sample and then decides, okay, that's enough evidence. I'm going to believe that the hypothesis is wrong. So we have a hypothesis that the mean is 3.5 and some samples trying to show that it isn't 3.5. We call the original hypothesis the null hypothesis. And you'll see on the right, we write that with an H with a 0 because the null hypothesis says there's no change, there's no difference, there's no evidence. And we also have the alternative or the alternate hypothesis, and they use H1 for that, H sub 1. And that one says the mean is not 3.5. And so we ask, is our sample mean far enough away from 3.5 pounds to allow us to reject that original hypothesis? We don't expect our sample mean to be exactly 3.5 because of variation. So we need to set up a critical value where we say, if the sample is further away from the mean than that, then I'm willing to say that 3.5 is wrong. So if you see in the picture, there's two critical values, one if the laptop is too high and one if it's too low. So we set up critical values and rejection regions. So if the sample falls in that rejection region, we're willing to reject the null hypothesis. So the evidence that our sample data gives us is as strong as its difference from the null hypothesis and the size of the sample. If your sample is far from that hypothesis, you're willing to say something is really different. The hypothesis is wrong. Or if you have a really large sample. So instead of saying 20 laptops, I took 1,000 laptops. and the samples and the average was lower, then you'd be like, well, that's a really big sample, so I think it's lower. So those two things help us. So to quantify this doubt or lack of doubt, we use probability. How likely is it we could randomly get a sample like we got? A sample that extreme? Is it unusual enough that we're willing to be wrong if we just happen to get a wonky sample? The probability that the null hypothesis is true and we get such an extreme sample is called the p-value. That's a really important definition. So if the null hypothesis actually is true and you got your sample, the probability that sample would happen is called the p-value. The critical value is the point at which we say it's extreme enough. My sample's weird enough. And the critical region is also called that rejection region, where we'll accept evidence of an extreme sample. Example for the mean. According to a Nielsen Company audience report, an adult person in the US spends about 10 hours and 39 minutes each day on screen time, clearly pre-COVID. The average of 10 hours and 39 minutes, or 639 minutes, includes our daily use of smartphones, computers, video games, radios, tablets, and TVs. It is believed that students at your community college spend more time on screens each day than 639 minutes. So students in your class use a survey that asks 25 students to record their screen time and record a mean screen time from all those students of 655 minutes with a standard deviation of 41 minutes. Any questions so far? Okay. So question, is this unusual enough to provide sufficient data, sufficient evidence that the screen time of your community college students is more than that recorded for adults in the US? Or is this result too close to the old result to say that it's statistically significant? Here's one for the proportion. According to the National Census, 24.5% of all US residents who live in renter-occupied housing units lived elsewhere 1 year prior. Because needing to move while attending school is believed to negatively impact student success, your community college decides to learn if the rate of moving is less for its students. A random sample of 1,004 students results in 228 who moved in the past year. Is this enough evidence to provide, is this unusual enough, to provide sufficient evidence that the rate of moving for your community college students is less than the national rate of 24.5%? Or is this result too similar to the old result to make a conclusion about the difference? So we don't say that our result is not enough evidence, so it's wrong. It just says we don't have enough evidence. So the outline for hypothesis testing are 4 steps. Step 1, state a hypothesis regarding the population mean or the population proportion. We're going to do hypothesis testing for other types, and there's all different types, but we're going to start in this chapter with population mean or population proportion, just like we did. We're going to collect data and compute the sample statistics, sample mean or sample proportion, sample size, things like that. We're going to analyze the sample data to assess if the data is sufficient to make a conclusion. And then we're going to state the conclusion. We're going to start with step 3, how to analyze the sample data. So again, the level of significance, this is not again, this is new. The level of significance of a hypothesis test is determined by the researcher and is denoted by alpha, a new Greek letter, alpha. It is at this level at which we're willing to accept an incorrect conclusion due to the unlikelihood of the sample. The critical value of the variable is defined by that significance level. If our sample estimate falls in the critical region, then it's extreme enough to reject the null hypothesis. The test statistic is the z-score for proportion, or t-score for mean, of the sample estimate. StatCrunch will calculate that for you. So it's going to do the z-score. And we know that when we're talking about unusual, we're often talking about we have to be within 2 standard deviations. So we'd want a z-score should be more than 2. Again, the p-value. The p-value of a hypothesis test is the probability that your random sample is so extreme that you'd have to be making an incorrect conclusion to say things have changed. So to perform the analysis of hypothesis testing, we want the p-value to be less than alpha. So alpha where is it? Down here. Don't know what's happening. I'll just say it. Alpha is the area of this critical region. And we want our p-value, our sample p-value, to fall in that critical region. So we want that p-value to be less than that area alpha. So if the p-value is less than alpha, we reject that things are the same and accept that there's a change or a difference. There are 3 types of hypothesis tests. We may expect the sample to be larger or smaller than the parameter, or we may not know if it's larger or smaller, and we just want to say it's different. And that leads to 3 types of tests: a left-tailed, a right-tailed, or a two-tailed. First, a left-tailed test. We're trying to show that a population parameter is now less than before. We're expecting our sample data to be smaller, our sample mean, for example, to be smaller than the population mean. So the critical region is seen in the left tail and has an area equal to the level of significance alpha. We can reject the idea of no change or difference. We can reject that null hypothesis if the probability is less than alpha, that a random sample statistic is less than or equal to our sample statistic, which means our sample statistic falls in that critical region, that rejection region. A right-tailed test is when we're trying to show the change or difference is now greater than the population parameter. So we have a critical region in the right tail, and it has an area equal to the level of significance alpha. We reject the idea of no change or difference if the probability is less than alpha, that a random sample statistic is greater than or equal to our sample statistic, which means, again, that our sample statistic, our sample mean, our sample proportion, falls in that critical region, in that rejection region. A two-tailed test is when we're trying to show a population parameter is now different than before. So the critical region is on both sides, both the right tail and the left tail. So it's called a two-tailed test. The total area, again, is equal to the level of significance alpha. So each side needs to have an area of alpha over 2. We reject the idea of no change is if the probability is less than alpha over 2, that a random sample statistic is either greater than or equal to our sample statistic, or it's less than or equal to our sample statistic. So our sample has to fall in one of the 2 critical regions. So as you begin conducting a hypothesis test, you ask yourself these questions. What's the population parameter you're trying to determine? In our case, it's either going to be a proportion or a mean. What's the required level of significance alpha? And is the test right-tailed, left-tailed, or two-tailed?